This video is about Dalton's atomic theory. Um, Back several thousand years ago in Greece, there was a man named Democritus who had initially proposed an atomic theory about the makeup of matter, but it really didn't catch on. And in fact, the idea of sort of the elements being earth, wind, fire, and water really held up for quite some time. And in fact, as recently as 300 or 400 years ago, people just really didn't understand what was going on with chemical reactions. But some things began to develop that led a man named John Dalton to propose his atomic theory. One of these was what came to be known as the law of conservation of mass. And so I'll read this out to you. The total mass of substances present at the end of a chemical process is the same as the mass of substances present before the process took place. Now, this wasn't always obvious to people, and let me just stop the show for a second and show you. And the classic example of this would be combustion. And in fact, when you burn, say, a house down that's made of wood, you start with this big giant house, and when you're done, all you have is a relatively small pile of ashes. It's difficult to see that mass is being conserved in that process because this big giant house is just being reduced to a small pile of ashes. People didn't really understand gases and the nature of air, and did not have the ability to measure the masses of things. I'm just going to show you because I know people like to see stuff like this. A quick example of something essentially disappearing when you burn it. So this just basically tends to make it look like you can make matter disappear. This is burning gun cotton. Right? So there is just right before your eyes a process that um, appears to make matter just disappear and go away. And so one of the early theories, or not early, but that sort of dominated from the 1600s to the early 1800s, was this idea of what was called phlogiston, that that something that was flammable contained this substance called phlogiston, but it didn't really have mass. It was kind of a strange idea because it would what would happen when you burn something, and you think about if you burn something, there are all these flames that obviously look like they're trying to get out of whatever it is you're burning. So that sort of principle or ether was called phlogiston, and it took the mass away, but nobody really had a very good idea about where that mass went because phlogiston was not necessarily considered to be a substance with mass. It was just sort of a burning principle. Well, over time, as scientists began to develop the ability to weigh things accurately and do things inside a sealed container, it was really proven that the total mass of the system after the reaction was over was equal to the mass of the system before the reaction began. And so that was a key thing that led to Dalton's atomic theory. Another thing was the law of definite composition, or sometimes known as the law of constant composition. And that simply says that all samples of a given pure substance contain the same elements in the same proportions. And so we can look at some very simple examples of that. If we look at water, every sample of water, no matter where it is taken from and how large or small a sample you make, as long as it's pure water, it's always going to be 88% oxygen and 88.8% oxygen and 11.2% hydrogen by mass. If we take pure sodium chloride, table salt, again, regardless of the source, as long as it's been purified, and we look at its percent composition by mass, it's always going to be 60.7% chlorine and 39.3% sodium. Then there was another thing that chemists began to discover as they looked more closely at various pure substances that were composed of various elements, and that was what's called the law of multiple proportions. And at first, this is a little bit maybe difficult to understand what it means, but I'm going to try and deconvolute it for you. So here's the statement of it. If two elements A and B can combine to form more than one compound, the masses of B that combine with a given mass of A are always in the ratios of small whole numbers. So what does that mean? Well, I'm going to give you an example. And so let's take a look at an examples of compounds of nitrogen and oxygen. That is pure substances that consist only of the elements that are compounds that consist only of the elements nitrogen and oxygen. And there are many, 6 or 7 different compounds of nitrogen and oxygen, probably more. I'm going to focus on 3. We'll call one of them compound A. And if you do an analysis of this by mass, you find that it's 63.6% nitrogen and 36.4% oxygen by mass. If you look at compound B, you find that it's 46.7% nitrogen and 53.3% oxygen by mass. And if you look at compound C, you see that it's 30.5% nitrogen and 69.5% oxygen by mass. Now, you may not be looking at this and seeing any small whole number relationships at all. But what would happen if we looked at these numbers and said, what mass of oxygen in each of these compounds, what mass of oxygen will combine with 1 gram of nitrogen? And so to get those numbers, you simply take A and you divide both sides by 63.64. You take B, you divide both sides by 46.68. You take C and you divide both sides by 30.45. That will tell you in each case what mass of oxygen will combine with 1 gram of nitrogen. And so when you do that, you find out that for compound A, 1 gram of nitrogen is in combination with 0.571 grams of oxygen. In compound B, 1 gram of nitrogen is in combination with 1.14 grams of oxygen. Compound C, 1 gram of nitrogen is in combination with 2.28 grams of oxygen. Again, you may not be seeing small whole numbers here, but if you look carefully at the relationship between these, and the easiest way to do it is simply to take all 3 and divide them by the smallest one. If you take all 3 of these numbers and divide them by the smallest number, what you get is 1, 2, and 4. And so this is essentially saying that the amount of oxygen that'll combine with 1 gram of nitrogen, if we look at these 3 compounds, those 3 compounds wind up giving a series of masses that are in a small whole number relationship, which is what the law of multiple proportions says. What are those 3 compounds we just looked at? Compound A was what's called nitrous oxide or laughing gas. Compound B is nitric oxide or nitrogen monoxide. Compound C is nitrogen dioxide. And you can see that if we normalize this to 1 nitrogen atom, for every 1 nitrogen atom, there's half an oxygen. For every 1 nitrogen, there's 1 oxygen. For every 1 nitrogen, there's 2 oxygens. That comes out to a ratio of 1 to 2 to 4. Let's take a look at Dalton's atomic theories. And this is the idea then, and really this helped to explain these observations. None of those observations I just described to you actually scream out at you, oh, there's such a thing as an atom. But he had the insight to put a lot of these things together that were going on in his time and devise what he called his atomic theory. And so let's go through what the postulates of that are. And this is right out of your textbook, and then I'm going to give you a slightly different version of it from the Wikipedia version. So each element, again, if you remember from chapter 1, elements are defined as being substances that cannot be broken down chemically into anything simpler. They're just simply the fundamental building blocks of matter. Each element is composed of extremely small particles called atoms. And so we're really going to just think of an atom as being a sphere, a solid sphere. In this case, they're using nitrogen and oxygen as an example, and so oxygen is being shown in red, nitrogen is being shown in blue. So each element is composed of extremely small particles called atoms, and all atoms of a given element are identical to one another in mass and all their other properties, but the atoms of one element are different from the atoms of all other elements. And so what they're showing you here is all oxygen atoms are the same. They're all red in this particular example. All nitrogen atoms are the same as each other. They're all blue in this particular example. But all atoms of oxygen are different from all atoms of nitrogen. The third postulate is that you can't change atoms of one element into atoms of another element in a chemical reaction, and you can't create or destroy atoms in a chemical reaction. So you can't convert oxygen into nitrogen, You can't make oxygen go away. You can't make oxygen appear. You can't make nitrogen go away. You can't make nitrogen appear. What you can do is, in a reaction, cause them to combine in various ways. So compounds are formed when atoms of more than one element combine, and a given compound always has the same relative number and kinds of atoms, which is really just kind of a restatement of the law of definite composition. So one of the things that's not mentioned in these slides is, well, let me not go there yet, but let me just end the show and go over here and show you um, the Wikipedia statement of Dalton's theory. The main points of Dalton's atomic theory are: elements are made of extremely small particles called atoms. That was the same as the first point in the slides. Atoms of a given element are identical in size, mass, and other properties. Atoms of one element, atoms of different elements differ in size, mass, and other properties. So in other words, all the atoms of nitrogen are the same as each other, but they're different from all the atoms of oxygen. 3 and 4 were kind of combined into a single point in the slides. Atoms cannot be subdivided, created, or destroyed. And then atoms of different elements combine in simple whole number ratios to form chemical compounds. What was missing from the slides is what's happening in a chemical reaction. In a chemical reaction, atoms are being rearranged, they're being combined, or they're being separated, but they're not being created or destroyed. Okay, back to the slides. One thing I want to point out to you, because this will come up sometimes in questions about Dalton's theory, and that is that Dalton actually didn't know anything about subatomic particles, which, by the way, is what you're going to learn about next. Dalton knew nothing about subatomic particles. He pretty much viewed atoms as being somewhat akin to just solid ball bearings, and say nitrogen ones just had an N sort of stamped into them, and oxygen ones had an O stamped into them, and carbon ones, et cetera. Somehow they had an identity, but he had no idea what gave them their identity. And so, since he didn't know anything about subatomic particles, he didn't think that atoms could be further subdivided. As far as he was concerned, they were the smallest building blocks of matter. And he didn't understand the idea of isotopes, which you'll learn about later in the chapter. That is, that some atoms of the same element can have slightly different masses. And so it's important to be careful when you're answering questions about Dalton's theory. I will often see test questions that ask you which of the following are tenets of Dalton's atomic theory, and one of the answer choices will be atoms are made up of protons, neutrons, and electrons, which is true, but that was not part of Dalton's theory. He didn't know about that. So it's just important to remember what he knew and what he didn't know when you're answering questions about Dalton and atomic theory. So that's the end of this short video. Thanks so much for watching.